So the next section is a shift from parametric and vector to polar coordinates and to polar functions. And we're going to be taking derivatives of polar functions today. Before we do that, I want to make sure you remember how polar functions work, or how polar coordinates work. Polar coordinates are going to be the magnitude and the direction. So the magnitude will be the distance to the origin, sometimes also called r. And the direction will be like the direction on the unit circle, so that's called theta. I always feel like these are written backwards. I feel like I would like to see the theta first and the r second, but that's not how polar coordinates are written. So we're going to just look at the theta first when we graph these. So if I'm going to graph point A, I'm going to point in the pi over 2 direction. And then from there, from the origin, I'm going to go 4 out. 1, 2, 3, 4. And so here is point A. I want to point out that that is how you would describe point A in polar coordinates. You could describe point A in rectangular coordinates as 0, 4 in rectangular coordinates. If I'm doing point B, I'm going to point in the pi direction, but then I'm going to go backwards 3. So I'm going to go 1, 2, 3, and there's point B. You might realize as I do that, first of all, B in rectangular coordinates would be 3, 0, and also that there are other ways of describing B. I could have described B as 3, 2 pi. Point in the 2 pi direction and go 3 steps forward. There are actually infinitely many ways to describe all of these points. All right, point C is going to be at point in the 3 pi over 2 direction and then go 1 unit, so here's point C. And then point D, we would point in the negative pi over 4 direction, and then we're going to go forwards 2. So that's just a review of how polar graphing works. Notice that we're not graphing in a different plane. It's the same plane. It's just a different way of describing those points. It's still in the same XY plane that you're used to. If I want to sketch a graph by hand, what I do is I work my way around the unit circle and figure out what r would be at each of those points. So I'm just going to plot a bunch of points. So if I start with theta equals 0 here, if I start with theta equals 0 here, I have 2 times cosine of 0, so that would be 2. So pointing in the 0 direction, I go 2. Here's where my curve begins when theta is equal to 0. Then if I go to pi over 6, I get cosine of pi over 3, which is a half. So I have 2 times a half, which would be 1. So then I'd be here. Then I'm going to do pi over 4. That would be 2 times cosine of pi over 2, so that'd be 0. So in the pi over 4 direction, I'm at the origin. And so my curve looks like it's going like this, at least so far. And I don't really want to do pi over 3 because then I'd have to do cosine of 2 pi over 3, which is going to have a root 3 over 2 in it. I don't really want that, so I'm just going to move on to the next pi over 6 thing, or the next pi over 3 thing. So I'm going to do, well, I can do pi over 2. So pi over 2 would be negative 2. So then I'd be here. And then I'm going to do 3 pi over 4. So that would be 0 again. And then I might be able to figure out what's going on, but maybe not yet. So then I would do 5 pi over 6 again. 5 pi over 6 would be cosine of 5 pi over 3 would be positive a half, so we'd be at 1. So in 5 pi over 6 direction, we'd be at 1. That's 2. That's why that looks weird. And then when we're at pi, we'd be at 2 times 0, so pi would be at 0. And I don't know if you can see, but we're starting to trace out a rose shape. And we'd finish that rose when we got back to 2 pi. And this gives me an idea of how the shape gets traced, and it gives me a picture of what that graph looks like. This is a function of theta, because every theta gives me an r value. This is not a function graph because it would fail the vertical line test. So in rectangular coordinates, it wouldn't be a function, but in polar, it is a function. You can also use your calculator in polar mode to graph these things, so I'm going to show you how to do that. So if we want to graph r equals sine of 6 theta, we grab our graphing calculator and we open up a graphing window. And if you go Menu, Graph Entry Edit, we can choose polar in that format. So we're going to do sine of 6, and then theta, I believe, is on this pi button. Yep, there it is. When I graph that, it might be not super easy to see, but I can change my window size just like always. And I'm going to go from -2 to 2. And there's our rows. And then if I wanted to graph that other one, that one would be 1 minus 2 cosine theta. And I can see the shape there of that graph. And so you can use your calculator. One thing to be aware of is you still kind of want to know how this got traced out, and you can always figure out how it got traced out by saying, well, if I'm at cosine of 0, then, or if I'm at 0, that would be 1 minus 2, so I'd be at -1. So actually this curve started over here at -1. All right. So we can also take derivatives of polar curves. We could take a derivative of r with respect to theta, and that's going to tell us the change in distance from the origin as the angle changes. We could take a derivative of x with respect to theta. That's going to tell us the rate of change of the x-coordinate with respect to theta. Same thing for y-coordinate. And then if we want to get the slope of the tangent line, that has nothing to do with theta. The slope of the tangent line is going to be dy dx. So if you are given a parametric function and you want to figure out the slope of the tangent line to the curve, you first want to convert to parametric. And so this is how you do a conversion from polar to parametric rectangular. You do x equals r times cosine theta. That's going to give you your x-coordinate. And you do y equals r times sine theta to get your y-coordinate. And then you figure out the derivative the same way we did for dy dx, the same way we did for parametric. It's going to be, we called it dy dt when it was parametric, but our independent variable here is theta. All right, so we're going to do this one. So we're going to write r equals sine theta as a parametric equation. So it would be x equals sine 2 theta times cosine theta, because it's r times cosine theta, and y equals sine 2 theta times sine theta. So that's our conversion. And then we want to write the equation for the tangent line at pi over 6. So first we need to figure out, first of all, let's figure out what point we're at pi over 6. So we'd be at x equals sine of pi over 3 times cosine of pi over 6. So that would be 1/2 times root 3 over 2, so it would be root 3 over 4. And our y-coordinate would be sine of pi over 3 again. I lied. Cosine of pi over 6 is 1/2, so this would be 1/4. Sine of pi over 6 is root 3 over 2. So if we're writing a tangent line, we need three things. We need an x-coordinate, we have it. We need a y-coordinate, we have it. And we need a slope. So we need to figure out dy dx. So dy d theta is product rule. So cosine of 2 theta times 2 times sine of theta left alone plus sine of 2 theta left alone times cosine of theta. And then we're going to take that and do dx d theta. So dx d theta is going to be the derivative of sine is cosine, and then leave cosine alone, and then leave sine of 2 theta alone, and take the derivative of cosine. Don't go crazy trying to simplify that because you have a number to plug in. We're going to plug in pi over 6. So cosine of pi over 6, pi over 3 would be root 3 over 2 times 2 times sine of pi over 6, which is a half, plus cosine of pi over 3 times cosine of pi over 6, cosine of pi over 6, pi over 3 times 2 times cosine of pi over 6, and then sine of pi over 3 times sine of pi over 6. And of all of that, I wind up with root 3 over 2 plus root 3 over 4. So 3 root 3 over 4 over 2 root 3 minus root 3 over 4 over root 3 over 4. And so that would be 3. So my slope is 3. So anyway, my equation for my tangent line is going to be y equals 3 times x minus a fourth plus root 3 over 4. All right. I have another example of a parametric that I'd like you to try. You're going to write the equation for the tangent line to this curve. I'm just going to have you pause the video and try it, and then the last little bit of this video will be the solution. So I wrote my x and y coordinates as parametrics using the r times cosine and r times sine. I found my x and y coordinates. They're not pretty, but I found them. I found the dy dx, which involved using the product rule or the chain rule, depending on how you wrote it. And then I plugged in pi over 4. This is kind of an ugly looking equation because it's got a lot of square roots of 2 in it. But I want to point out that it's correct, and I know it's correct because I graphed it. So I took my Desmos graph of 1 minus 2 cosine theta. I plotted the point where we are at pi over 4, which is this point right here. And then I graphed that tangent line, and I can see that that tangent line is touching the slope at that point and has the slope of the curve. All right, that is parametric. I mean, it is polar. It's finding derivatives of polar functions. Good luck today.